Hello, everyone. Welcome to the fourth webinar in our series, Achieving Warranty Cost Reduction Goals with Effective HALT&HASS. I'm Tom Peters, Director of Professional Services, and I'll be your moderator for today. Today's topic and guest presenter is John Hansen with Varian. We have organized a webinar series to provide a comprehensive overview of setting up and running an effective accelerated stress test program that will deliver tangible results in support of warranty cost reduction programs. Today's session covers effective HASS and is a case study by Mr. Hansen and his experience setting up a HASS function at the Varian facility. John is the Director of Reliability at Varian in Salt Lake City and has a long history in directing all aspects of reliability, implementation, and management and risk analysis. Today, we're going to talk about Varian and their experience. And John is from the facility in Salt Lake City. Today's webinar is on effective HASS, and this is in the application of medical imaging. And at this point, I will let John Hansen take over and relate his experiences to us. John?
Yes, thank you, Tom. As Tom mentioned, my name is John Hansen. I represent Varian Medical Systems. We'll start by telling you a little about Varian. We're headquartered in Palo Alto, California. There are three main business units. We have oncology, basically cancer treatment, X-ray products, and security and inspection products. As Tom said, I am with the X-ray product division. We do medical X-rays for both OEM, custom design. We do industrial X-rays, and we do digital radiography. And as part of digital radiography, we do flat panel image detectors. Now, just a real brief explanation of what these flat panel digital detectors are. They basically replace a film cassette in an X-ray system. So that's the kind of thing that we build here. That's the kind of thing that we'll talk about today. As I said, we're from Salt Lake City. And with that, we'll just get right into the presentation. The things we want to talk about today are as follows. We want to talk very briefly about our reliability program. We want to give some background as to how HASS fits into our reliability program. As part of that reliability program, we have three main aspects. One is design for reliability. One is what I will call manufacture for reliability. And the third is post-market reliability support, or reliability assurance, if you want to call it that. Design for reliability. What do we mean when we talk about design for reliability? What do we do in design for reliability? Good reliability has to start out with knowing what you want to accomplish. We need to have correct specifications, and we need to have those specifications allocated during the design phase to the specific feature or specific component that we are analyzing. We need to understand what's needed from a reliability perspective. We need to understand what our customers demand, what they need, what they expect. We also need to understand what's possible. That's a bit of a technical analysis, and there needs to be a logical allocation of requirements to subsystems and components. I will diverge here for just a second. If we don't appropriately do allocations, if, for example, we just do a straight line allocation and assign every subsystem the same reliability requirements in order to meet the end goal, we are setting ourselves up for failure. There needs to be logic and understanding about what is needed and what is possible, not only for the system level, but for each aspect of that system. We need to have, and we expect to have from our design engineers, a robust design. We expect that components will be selected that meet our reliability requirements. We expect that as we do the design, we will have adequate derating. We also expect that as part of the design, we will be doing design analysis. Things like reliability predictions, failure mode effect analyses, and fault tree assessments. We'll talk in just a minute about how important these are as we go into a HALT and a HASS process, at least how important they are for our program. Also, as part of our design reliability, we have an element of accelerated life testing. I know we talked about HALT last session. We use HALT here. We use it in several different ways. We use it to understand what our design margins are. We use it to understand what the design weaknesses and the design strengths are. We also use HALT as part of our failure analysis approach when things don't go right exactly how we want them to go. We try to use this to duplicate the failures that we are seeing in the field to understand them better. There's also another aspect of failure analysis here that is very important. We use failure analysis as part of the HALT process. When we have a failure, we understand why that failure occurred. We understand the failure mechanisms as well as the effect that it has on our system. And we make a decision as to whether or not that failure is important to our design. Some failures may not be important. If you're testing well out of your operational ranges and you get a failure that is specifically related to the stress that it's seen at that level and will never be seen in useful life, we can make a decision as to whether or not that is important to us. We also, as part of our reliability program, our design for reliability program, use highly accelerated stress testing. We basically use this to confirm our reliability assessment, to understand through test, a step beyond prediction, what our reliability entitlement of the design we're using is going to be. We base our HASS testing on our HALT results. In other words, we understand what our limits are, and we back off from those limits to a point where our HASS testing is realistic and provides a result that is and has proven to be reliable. We use our HASS testing to predict field performance as well, to confirm our reliability prediction, to get a first look at what's going to be the case when this product gets out into the field. I will go next to our manufacture for reliability. Manufacture for reliability. What are the components of manufacture for reliability? I want to talk for just a moment about supplier reliability. In many cases, especially now, our reliability or the reliability of our product depends on the reliability of the components that go into that product. In our case, we have the circuit boards that go into our design, the power supplies, all the major components manufactured outside of our facility. So we need to be very careful to help our suppliers when necessary and to work with our suppliers to get the reliability of the parts that we need. We need to, when we're talking about reliability, we need to know what failed. We need to know why it failed. We need to know what actions we can do to prevent failure recurrence. And we need not to be afraid to ask for supplier corrective action. There is a characteristic I have observed among almost every engineer that I've known, and I admit to having the same prejudices that I'm going to talk about here. We all tend to think that we know exactly what's going on, or perhaps worse, that we know that it can't be designed, or that it can't be the manufacturing process, or that it can't be our supplier. When we are doing reliability testing, there can be nothing that's off limits. We need to be able to put our preconceived notions aside and let the test and the testing and the data speak for itself. HASS, highly accelerated stress screen. Why would we use HASS? What is it? We'll talk about what our definition of that is here in just a moment. I want to address the why question first. For us, in the medical device industry, any failure of our product is a critical failure. Anytime our product is being used in a medical procedure and doesn't operate the way it should operate, it's a problem. And so we can't afford failures. Especially, we can't afford infantile failures. HASS in general is aimed at eliminating those failures prior to the product ending up in the hands of the end user. In other words, keeping the failure in-house. We'll talk a little bit about how we implemented HASS. We'll talk briefly about failure analysis and how it applies to HASS. So, why HASS? The chart you're seeing is a chart of one of the products in our product line. You will notice a very small infantile failure rate. That infantile failure rate was something that we chose to eliminate. Prior to implementing HASS at our facility, we were using a burn-in process. A fairly extensive burn-in process, by the way, that removed most failures from our product before it went into the hands of our customers. But we saw infantile failures, and we set out to eliminate those infantile failures. As we attempted to do that, we realized that highly accelerated stress screen may be an effective way for us to eliminate these failures. So what do you need to know when you're implementing HASS? What are some of the important things? You need to understand your product. You need to know how the product can fail, what the failure mechanisms are going to be. You need to understand what your most critical failure modes are. In other words, you need to do a FAMICA, or perhaps a fault tree will be adequate. We chose to do both a fault tree and a FAMICA. Let me explain briefly how and why we did that. In the early part of the design, before the design really comes together, before it is set in stone, we went through, or like to go through and do a fault tree assessment to understand at a very high level what can fail in our product, what is likely to fail in our product, and what the effects of that are going to be from a very high level. We use the fault tree tool to do that. Now, it's not perfect, but it gives us initial information in order for us to understand what we need to be concerned about in the design. After the design has progressed to the point where we believe we have a system, a subsystem, a set of product that is where we want it to be, then we do a failure mode effect analysis. We, because of the importance of our product and the importance of failure avoidance, like to do the failure mode effect analysis to the component level. In other words, we understand the likelihood of each component failure, and we understand from an analytical point of view what those failures are likely to be and what those effects are likely to be in our product. Then as we move into development testing and understand what actually happened when we put this system together and begin testing it, we start to understand even more in depth what the failure modes of this system are going to be. We understand what we need to eliminate, or what are the potential infantile weaknesses of our product. And of course, with HASS, whenever there is a failure, like to do a failure analysis. A failure analysis of the development failures gives us insight into what we need to do as we move into HASS testing. Now, the next piece that we had to do as we went into HASS implementation, is to choose our appropriate stresses. Our product line has some things that are very unique. We won't get into some of those today, but those stresses that we see may be mechanical stresses, like we would talk about in a typical HASS type test, of where we apply a mechanical stress to produce or to eliminate weak failures, to precipitate any latent defects. We have, and it has been my experience that it is also important to use other types of stresses as appropriate. For example, voltage stress may be an important stress to apply. In some cases, a current stress may be an appropriate stress to apply. One of the things that I feel very strongly about as far as HASS testing is this should be a tool that is used to improve reliability, to enhance reliability, to optimize reliability. But we shouldn't see it as the only thing that is important in a reliability program. It is a tool, nothing more, nothing less. An important tool, one that has been very effective for us, and I believe can be very effective for everyone, but just a tool. Failure analysis is another important tool. And as we will discover, as we have discovered, appropriate corrective action is critical to the successful implementation of a HASS program. So how did we do it? As we went through and we decided that we needed to implement a HASS program, we began looking for chambers. There are a lot of HALT&HASS chambers out there. We had some unique requirements as far as what our HASS chamber needed to do. We needed to be able to operate our equipment as it's undergoing the HASS process. We needed to be able to have a relatively high throughput, because it is our intention to put all of our product line initially through a HASS process. So we looked for what was out there, makes for us was the best fit. You can see what our setup is. This is a setup that you're looking at. It has 6 separate compartments. We chose to use 3 panels per fixture, so in total we can do 18 panels at a time. What were we able to do? We were able to eliminate out-of-box failures. We were able to improve our throughput. to move from 120-hour burn-in to an 8-hour burn-in for HASS. This has allowed us better feedback to our suppliers, and it has improved our key customer satisfaction. Now, the point where we are right now is that we have contained the failures that are occurring. That's not the end of the road. Once the failures are contained, we need to eliminate those failures at the source. Our HASS program has allowed us to begin doing that, to begin, as we understand what failed, to implement corrective action at suppliers and in our own processes to eliminate the source of the failures. It's interesting to note that many of our suppliers are surprised at the fallout that we get of their product as it goes through the HASS process. We believe that as we progress, we will be giving requirements to our suppliers to eliminate infantile failures. We may not, and I emphasize may not, we have not decided yet, we may not require them to do highly accelerated stress screening. But quite likely there will be provisions in the contract that contain a financial penalty for certain levels of reliability that don't meet our needs. So, in other words, we may be providing an incentive to our suppliers to do whatever it takes with their equipment to make sure that the failures are eliminated and contained before they come to us. That's one of the key things that we can do through a HASS process to push back and to solve the source of the failures. I wanted to mention briefly electrical stresses and their importance in a HASS process. I will use a case study. It's not something that we have a slide for, but I will describe it as we go along. In this case study, we had gone through and created what we thought was a very robust design. On paper, the design looked robust. As we put it through all of its technical testing, the design performed perfectly. As we moved to environmental stresses in a HALT program, once again, the design performed perfectly. However, when we varied the voltage on a particular component, a particular high voltage component, all of a sudden we were having failures in the IGBT circuit. And it surprised us. It surprised us a great deal. It surprised the supplier of the IGBTs as well. But as we dug into that, the supplier of the IGBTs recognized a problem in his production, in reality in his design. In fact, his component did not meet the requirements of their spec sheet. Everything had looked good, but as soon as we applied that one particular stress, then things no longer looked good. Had we put that product out into the field, it may have worked fairly well for the most part, but because of that weakness in the design that was discovered through a HALT process, then if we wouldn't have fixed that, I am convinced we would have had failures in the field. Now, why do I say that? We went, in this particular case, to a HASS profile. And we started having about a 10% fallout of the IGBTs in HASS before we corrected the design. A few of those products did go out into the field before we corrected the design. We had about a 10% failure rate in the field of that particular product. But as soon as we recognized the problem through appropriate testing and made the appropriate design changes and corrections, and as soon as the supplier made the appropriate design changes and corrections, the problem went away. The point I want to make here is that HASS can and does help us eliminate problems in the hands of our customers. So, what do we do after we have completed HASS? When the processes are in control. Let me talk about for a minute what I mean when the processes are in control. An in-control process ensures that the components we put into the process are adequate for the design. It ensures that our manufacturing technique is appropriate for the design. In other words, when a process is in control, then we will not be producing failures. We will have eliminated infantile failures. I do believe that this is possible. So, when processes are not yet controlled, when we're not in that state I just described, then I believe we should and we will continue to use HASS to protect our customers. During that time, we will solve the remaining issues. Again, nothing is off limits. Design, manufacturing, supplier issues, nothing can be off limits. We need to be able to understand and solve problems with an open mind. So what about when processes are in control? When we have demonstrated through test, through field experience, that we are producing product at the quality level we need. At that point, we could and should consider going to what I will call a highly accelerated stress audit. In other words, not everything goes through HASS anymore. We take a sample of product, we run them through HASS, we make decisions based on the results of that sample. If we are in control, as we think we will be, then we will not have fallout during the HASA process. However, if something has changed in the design or in the process, and we are no longer producing the quality of product that we believe we should, then that will show up during the test and will kick off the corrective action cycle. That's what we intend to do. That's what our program allows us to do. So, I want to talk for a minute about post-market support. What do I mean by post-market support? After a product has left the factory and after it goes out into the hands of the end item users, we still need to understand what happens with that product. We need to understand how often our customers are seeing failures. We need to understand what failures are occurring. We need to understand why the failures occurred. The scenario I'm talking about is this. We have sent out a product that we think is the best that it can be. But we still have an obligation to monitor that product's performance. We have an obligation to our customers when we're in the medical device industry. We have an obligation to ourselves from a financial standpoint. We need, in the post-market scenario, to be able to take appropriate action. Knowledge without action is kind of pointless and of limited value. Every failure has a cause. Something happened, and we can't understand that. We need to understand that. We need, once again, to be not afraid to work with suppliers. HALT may be appropriate for failed product as well as new product development. for example, if we are seeing failures in the field that surprise us, let's put it that way, and we need to understand them as part of the root cause analysis and corrective actions system that we employ, it may be in our best interest to go back into the HALT cycle, to go back in reality to the full HALT/HASS cycle. That's what we intend to do. It has been, I will say this for us, it's been an adventure as we've gone through the HASS process. We have learned a lot. We have changed our product. We have changed our manufacturing processes. We have changed those things that are appropriate to change. And I want to mention briefly the cost effectiveness of being able to do this. As we look at our warranty costs for the products that we have put into HASS, in the less than a year that we have had the HASS process in place, we have saved more than the cost of the equipment in warranty cost alone. We have also had been able to increase our production quantities without increasing manufacturing staff or test staff appropriately. So we have been able to have some very good results for us. Not only has it given us good rapport with our customers, it's given us cost savings, it's given us knowledge for improving our next generation of the designs. So that is pretty much the end of my presentation. I guess now is the time for questions.
Okay, John, thank you.
I'm here.
Okay, thank you, John. There's been several questions, and we'll take those in order as we can. And one comment is that some of them are having a little bit of trouble hearing you. Their phone lines are not as good quality as some of the others. But one of the first questions was to define HASS, H-A-S-T. Typically the usage of HASS is using an autoclave type test equipment. Would you please define how you use HASS?
Yes, the way we use HASS, once we understand the destruct limits and the operational limits of our equipment, we are in a position to use highly accelerated stress test. We use this to actually verify the reliability of the product. So basically we back off from our destruct limits to a stress level that is not destructive, but still applies an aging stress to our product. And we test our product at this accelerated stress level to understand really the long-term performance of our product. We can, under certain circumstances, which I'll talk about, use that to actually verify things like failure rate and MTBF. We can use that to verify our performance, the performance characteristics of our product. Now, as we go through this testing, we can, in effect, understand the life characteristics of the product. So, rather than test to the full MTBF, sometimes we just test to what I will call the B10 level, or the 10% failure rate, rather than the mean time between failure, just to ensure that we are getting where we need to be. I hope that answers the question. If it doesn't, please let me know.
Okay, thank you, John. And the other question is, have you completely replaced burn-in with HASS?
We have completely replaced burn-in with HASS on the products that have moved to HASS. Now, what do I mean completely replace burn-in with HASS? By that I mean, I don't mean to say that we have quit running our product through its burn-in type testing. What I mean to say is that we have shortened that life, that burn-in time, burn-in so to speak, by combining that with mechanical stresses of the product. So we no longer have this 120-hour burn-in. We have now an 8-hour HASS cycle. But during that HASS cycle, we still functionally operate our equipment so that it's going through the paces that it would normally be put through under all the temperature extremes, high and low temperature, vibration, everything else. So yes, in that sense, we have replaced burn-in with HASS.
Okay, thank you. Another question is, in slide 19, you mentioned 10% fallout during HASS testing and about a 10% failure rate in the field. Shouldn't HASS have caught those field failures?
Perhaps I didn't express myself clearly. We, during that process, were undergoing, with the company that I was at the time, we were undergoing basically a verification of the HASS process. So we found the problem in our HALT testing. We found a problem, an electrical problem in our HALT testing. There was some desire with that company to say, well, it's good enough, it meets our specifications. So a low rate production was released to the field. At the time, they wanted to run half of the devices through a HASS process, and they wanted to say, okay, burn-in's just fine for the others, and it's going to be okay. What I meant to say is that when we implemented HASS on the 50% of the product line, we found the exact same 10% of the failures during HASS as were occurring in the field and those that we didn't run through the HASS process. I meant to say that there was a correlation between eliminating failures in HASS and our performance in the field. If I wasn't clear on that, I apologize.
Okay, thank you, John. Another question is, what type of failures are you finding in HASS? Are you finding just process, or are you finding component failures? What type of failures?
You know, when you look at that from a physics of failure standpoint, I would have to say that they're all manufacturing failures. However, let me say this: we find problems with our own manufacturing process as we use some very unique processes to electrically attach to a glass plate. So we find those kinds of process problems in our own manufacturing process. We do have component failures. However, when you look at those component failures, then you can see that something typically went wrong during the manufacture of that component that created a weakness in that component that then fails during HASS, is then eliminated during HASS. So we do see some component failures, but typically those failures are things where something in the component manufacture process went a little wrong.
Okay, thank you. And one of the other questions is, when you've obviously had experience both burn-in and HASS, can you describe a little bit the differences that you see where you might use one over the other, or one has an advantage over the other?
Yeah. Once again, it goes to understanding your design, understanding what's likely to fail on your design, understanding what you're trying to accomplish. if you are attempting to eliminate latent defects, and I will say specifically manufacturing defects, then HASS works very well for doing that. I would always advocate that you test the device functionally as you're going through the mechanical stresses of a HASS process. There may be, based on the design and the kinds of things that you're trying to eliminate, a time when burn-in may be more important or may be more productive. But I have to say that I believe the best scenario is a functional burn-in type test as you're going through HASS.
Okay, thank you. What is the rough percent of failures that are seen in HASS versus burn-in?
Rather than answer that with absolute values, I will just say this, that we tend to see 15 to 20% more failures out of our HASS process than we were seeing in burn-in. I really would rather not get into the magnitude of what we have seen.
Okay, thank you. And I'm looking at a number of the questions here. Is it what HASS stress profiles have you used? Do you have an example? And I think I'll let you answer, but I think the generic answer depends on the product being tested. So I'll let you address it from your viewpoint, John.
Okay, and I can address that from our product line, which is probably the best way to do that. We typically will use a high temperature of 60 to 70 degrees C. We typically will use a low temperature of 0 to 10 degrees, 0 to 10 degrees C. We use a vibration for most of our product in the range of 50 to 70 G RMS. I've got Brent Scomo here with me, and I'm kind of looking to him as I answer the questions because he has actually been doing some of the testing. We, because of our product, use a relatively slow ramp rate, just because we know that some elements of our flat panel imaging devices can be damaged by rapid thermal change. So we're very careful not to do things that we know will damage our product. Now, into our product go several circuit boards. These circuit boards tested alone can most likely have a higher high temperature, a low temperature, and they can do the rapid thermal stress. So I mention this because it's important that as you go through the HASS process that you don't damage your product. However, it is also important to apply the highest level of stress that you can without damaging that product in order to eliminate failures. The thing with our slow ramp rate that we need to be worried about are solder joints, which are typically precipitated by a much more rapid thermal change. So I would say that on a HASS profile, on a typical circuit board, your levels, and once again, as Tom said, it depends on the product, but I would think that 80 degrees C for the high temperature would not be unheard of, that minus 20 to minus 30 degrees would not be unheard of, that the thermal change should be as rapid as your device can stand without being damaged. That's to set those limits are why you use the HALT process, by the way.
Thank you, John. And John is right in that there is some well-defined processes to obtain the limits and the process, the profiles that you want. Both the HALT guideline and the HASS guideline are available on the Qualmark website for download at no charge. If you want more detail how to accomplish that. And so you can go online and find that. And there will be a new revision of the HASS guideline released shortly within about the next 30 to 60 days. One of the other questions is, you talked about using HAST, H-A-S-T, results to calculate V10. Are you using your HALT chamber or HAST chamber to do that calculation?
To do the calculation, we will use our HALT chamber. We use our HALT chamber to do that. Right now, we have in our facility a very rapid release of a new product line, and so not every product we put out has gone through HAST. But we do use the HALT chamber to do that. One of the drawbacks is it can tie up the HALT chamber for a period of time. So we have in a couple of instances done that, gone through to calculate, to get the data that allows us to calculate a B10. And in theory, although we probably won't do that, you could run long enough to calculate an MTBF as well.
Okay, thank you. And the other mention is we'll be releasing a new white paper on HASS and life valuation of a product that is a very good paper describing the theory and practical aspects of determining a safe screen in HASS and how it affects the life of a product. That'll be coming out shortly also. And we had one other question about temperature capability of the chambers, and I'll answer that. The HALT and HASS chambers, depending upon which models you have a temperature extremes of minus 100 C up to plus 250 C. So they pretty much will span the temperature capability of about 98% of the product that you see out in the market today. One other question is, why are your fixtures red, John?
Okay. There are two major schools and major colleges in Utah. One is red, one is blue. I won't mention which is which. However, our fixture designer went to the red school, and so he made them red.
Okay, thank you, John. That's much appreciated. There's always a little local color and everything.